In this video, I'm going to talk about series solution for differential equation near a singularity. The problem I'm going to discuss is this one. 2x square y double prime plus 5xy prime minus 2 times 1 plus x times y is equal to 0. Our first step in solving this problem would be to express this equation in this format: y double prime plus p of x times y prime plus q of x times y is equal to 0. And it's pretty easy to do so. We divide both sides of this equation by 2x squared, and that gives me this equation. From that, I can easily figure out what is my p of x, which is 5 over 2x, as you can see right here, coefficient of y prime, and q of x is going to be the coefficient of y, which is this number, negative 1 plus x over x squared. Now, before we can solve this differential equation, we need to ensure one thing. We need to figure it out whether the singularity that we are dealing with, is it a regular singularity or an irregular singularity? If it is a regular singularity, then we can go ahead and find a series solution. If it is an irregular singularity, then we can't. Okay? So how do we figure out whether a singular point is a regular singular point or not? It's pretty easy. If these two limits exist, so let's say x naught is the point in question, whether this point is a regular singularity or an irregular singularity. What we do to figure that out, we take the limit x approaches x naught time x minus x naught times p of x. We take the limit of that. If that limit exists, as well as limit x approaches x naught, x minus x naught whole square times q of x. If both of these two limits exist for point x naught, then we call the point x naught a regular singular point. If one or both of these limits do not exist, then we say it's an irregular singular point. In our case, let's figure it out whether it's a regular singular point or not. The point in question, x naught, is actually equal to 0, right? So limit x approaches 0, x minus x naught is going to be x minus 0, which is just x, times p of x. We just found p of x to be 5 over 2x, which is this. If I take the limit of it as x goes to 0, it is 5 over 2. All right. If the limit exists at a point, we call it analytic point. That means, what does the word analytic means? It means that it has derivative in the complex plane. That's what it means, okay? Now, let's go ahead and do the same thing for the second limit. Limit x approaches 0, x squared times q of x, which is this, right? Negative 1 plus x over x squared. As you can see, as x approaches 0, it goes to negative 1 because this x squared and x squared cancel out. So both of these two limits exist for our singular point. Therefore, the singularity that we are dealing with is actually a regular singularity. So we can find a solution. Now, if you are dealing with a regular singularity, the solution will be of this format. Y of x is equal to x to the power r times summation n is equal to 0 to infinity a sub n times x to the power n. Now, I can go ahead and move this x to the power r inside the summation to combine this into a single term. That's going to give me summation n is equal to 0 to infinity a sub n x to the power r plus n. Now, this is my y of x. So this is my y of x. So what I'm going to do, I'm going to take the first and second derivative of it. Remember, we are making the assumption that this is the solution to this differential equation with singularity. Now, this is my y of x right here. The first derivative of it is going to be just this, r plus n times a sub n x to the power r plus n minus 1. Second derivative would be taking the derivative of the y prime, and that's going to give me this term. It's pretty straightforward. R plus n times r plus n minus 1 a sub n times x to the power r plus n minus 2. Now I have y, y prime, and y double prime. Since y is my solution to this differential equation, I'm going to go ahead and plug in these values into this equation. If I do that, this is what I get. It's pretty straightforward. 2x squared times this is y double prime, then 5x times this is y prime, minus 2 times x plus 1. So the x plus 1, so I break it down into two pieces. So 2 times 1 plus x is going to give me 2, then multiply it with y, 2y plus 2xy, okay? Now 2y, 2, and this is the y, the solution, okay? We are making assumption that this is the solution, that's just 2y, minus 2x. So this 2x times the solution itself, and all of it equal to 0. Now let me go ahead and pay attention to this interesting thing. So look at this x squared and x to the power r plus n minus 2. If you combine these two, it's going to give you x to the power r plus n. And the same thing here, if you look at this x and bring it inside the summation, this is going to give you x to the power r plus n, because r plus n minus 1 plus 1 due to x is going to give you r plus n. So in essence, these two summations, they have the same power for x. In addition, this one also has the same power, okay? X to the power r plus n. So the first three summations, they have x to the power r plus n, okay? So the variable x has the same power, so we can combine the first three summations by taking the coefficients, okay? If we take the coefficients together, we get this. So look, this one is this term, this one is the middle term, and negative 2 is this negative 2 times a sub n x to the power r plus n, then minus this term, okay? So minus this term. So one piece of information that you want to pay very close attention to is this: the power of x here. It's not r plus n, but rather it is r plus n plus 1. It's different than this one, okay? So what we are going to do, we are going to kind of shift the indices a little bit to make sure that this term or this summation also has x, where the power of x is r plus n. And the reason that we are doing it is to make sure that both the summations have the same exponent or power for x, so that we can combine the summations and compare the coefficients on the left for x with those of the right. That means compare the coefficients of x on the left to the coefficient of x on the right for the corresponding power of x. Now, how do we shift the indices? It's pretty easy. So look at this summation, all right? So you have x to the power r plus n plus 1. All you have to do is replace n by n minus 1. So every time you see n, you're going to replace it with n minus 1. So n minus 1 is going to be here. Here a sub n is going to be n minus 1. And then here n is going to be replaced by n minus 1. So if you replace n by n minus 1, what's going to happen here? So you're going to have x to the power r plus n minus 1 plus 1. So these two are going to cancel out. That's going to give you x to the power r plus n. Okay? So we are going to have summation. I'm going to write the x to the power r plus n first. Now look, I'm replacing n by n minus 1, right? So I'm saying instead of n starting from 0, I'm saying n minus 1 is starting from 0, which is equivalent to saying that n actually starts from 1. So that's going to be the case here. N starts from 1 and goes to infinity. And look at this little a sub n sitting there. Now a sub n, that has to be replaced by a sub n minus 1. Remember, I'm replacing everything, all the n's by n minus 1. So it's going to be a sub n minus 1. And then don't forget that 2. And that's how we get this term. Now, please note that the power of x in the first summation is r plus n. The power of x in the second summation is also r plus n. So we are good. However, there is a catch. The catch is this. This n starts from 1 and this n starts from 0. So to align both of the summations to start from the same point, that means n is equal to 1, we just strip the first term, n is equal to 0, from this one. So we take it away. Now, if we plug in n is equal to 0, what is it that we get? Okay, so we are going to plug in n is equal to 0 here for the coefficient. Okay, notice we are going to get a term a sub 0, but by assumption a sub 0 is not equal to 0. Okay, so a sub 0 cannot be 0, so that means this left side, this term within the square bracket has to be 0. If I plug in 0 for n within the square bracket, that means into this is what we get. 2 times r minus 1 times r. So 2 times r minus 1 plus 5 times r, because n is equal to 0. Remember, n is equal to 0 and n equal to 0, minus 2. So this is what we get. This is nothing but a quadratic equation in R, and it's very easy to solve. By the way, this equation that we got is also called indicial equation. Now let's go ahead and solve it. It's pretty straightforward. You can factor it, okay? And you know how to factor quadratic equations, or you can use the quadratic formula. If you factor it, you're gonna get two values for r. r1 is equal to negative 2 and r2 is equal to 1/2. Now r1 minus r2 is not an integer, or r1 is not equal to r2. So these are the two pieces of information you may want to keep in mind. If your r1 is equal to r2, if your r1 is equal to r2, that means roots repeat, right? The same roots. In that case, you will have a solution that's going to be slightly different, okay? And I will make a video for that as well. Now, on the other hand, if your r1 minus r2 is an integer, okay? An integer. In that case, your solution will be different too. And of course, I'll make a video for that as well. Now, the easy and nice case is this one, okay, where R1 and R2 are different. So we got R1 is equal to negative 2, R2 is equal to 1/2. Then my solutions are going to be pretty straightforward. Y1 of x is going to be x to the power negative 2 times summation n is equal to 0 to infinity a sub n x to the power n. Just to remind you here, we talked about our solution being of this form. Y of x is equal to x to the power r times summation n is equal to 0 to infinity a sub n x to the power n. Now I found the value of r. I just plugged in the value of r here, x equal to negative 2. Then we still have to find the a sub n's, that means the coefficients. And similarly, y2 is going to be x to the power 1/2, because r2 is 1/2. So x to the power 1/2 times summation n is equal to 0 to infinity a sub n x to the power n. Let's now go ahead and find the coefficients, and these two terms are pretty straightforward. This is something we already have had before, and if we strip off the first term from here, which we did, we are starting from 1, right? So we are starting from 1. So now I'm comparing apples to apples. So this and this coefficient. So if you take both of these coefficients, you're going to get this times x to the power r plus n, but on the right hand side you have 0, so that means any coefficient of x is going to be 0. So that tells me that these coefficients on the left must evaluate to 0. Then you just have to do some algebra and you need to get here. What we do here is very straightforward. I'm just trying to solve for a sub n. If I solve for a sub n, I'm going to get this. Look at the denominator, pretty straightforward. So denominator is a quadratic equation actually in r plus n. Okay, let's say we assume r plus n to be k, just for the sake of argument. Then the denominator becomes 2k squared plus 3k minus 2, and you can factor it out. If we factor it out, you're going to get k plus 2 times 2k minus 1. So, but k is r plus n, so that's what it is. So, r plus n plus 2 times 2 times r plus n minus 1. Remember, all of this has to be for n greater than or equal to 1, because n is equal to 0, we have taken care of separate. Now we have to take this recursive formula or recursion formula, okay, and apply it for two different values of r. Okay, one value would be r is equal to negative 2, and the other value is going to be r is equal to 1/2. Now for the first r, which should be r sub 1 here, is equal to negative 2, what do we get? What does this evaluate to? So you plug in the value of r to be negative 2, that's going to give you, the numerator doesn't change, right? It doesn't have any r. The denominator is going to be negative 2 plus 2, right? So negative 2 plus 2, which is going to give you the n, and plug it in here, negative 2, and simplify it, that's going to give you 2n minus 1. So your recursion formula is this: a sub n is equal to 2 times a sub n minus 1 divided by n times 2n minus 5. Now we have to do it for n is equal to 1, 2, 3, 4, 5, 6, etc. So for n is equal to 1, what do we get? So you plug in n is equal to 1, right? So this is what we get. A1 is equal to 2a0 over negative 3. For n is equal to 2, you get the following. You get a sub 2 is equal to this. Remember, a1 you already found in the last part, so you go ahead and plug it in. If you simplify it, your a2 becomes this. Similarly, you do it for n equal to 3. Again, that's going to give you a3, and you keep going forward. Remember, you have to use the last one, right? a2. So there should be an a2 somewhere here. Here is your a2, and then you plug it in and simplify, and you're going to get this. Similarly, you can do it for n is equal to 4, 5, and 6 by using this recursion formula. Now, if you take all of these coefficients and plug it into your solution, y1 of x is equal to x to the power r times this summation, and you kind of write out the summation and simplify it, and this is what you're going to get. By the way, in many cases, these recursion terms, you can find a general term, but I haven't taken the trouble to go ahead and find that general term. And also be very careful with these problems. If you make one mistake, okay, you'll end up repeating that mistake, and you're not gonna get the answer correct. It's very much possible because it's a very lengthy problem. Hopefully I haven't made any mistake here, okay? But it's possible, by the way. Now, remember, I'm trying to show you the process, how to solve the problem, not necessarily whether you got the actual coefficient 100% right or whatnot. Of course, you'd want to get everything right if possible, but follow the process. That's the most important thing. Then you'd be able to understand how to solve these types of problems. So now let's go ahead and repeat the process again. Last time we used the recursion formula for R1 is equal to negative 2. This time my R2 is gonna be 1/2. So I'm gonna go ahead and plug it in into this formula. If you do that, this and simplify it, this is what you end up getting at the end. So your a sub n is n minus a sub n minus 1 divided by n times n plus 5/2. We are going to repeat the process. We are going to do it for n is equal to 1. That's going to give you this. For n is equal to 2, that's going to give you this. Remember, as you progress through these coefficients, you're going to have to use the previous results, okay? In this case, you just go back 1. That's why we call it recursive formula, right? N is equal to 3 is a sub 2 divided by this number, but a sub 2 is something we already found. Plug it in, you're going to get this. Similarly, for n is equal to 4 and whatnot. Now, what do? You take these values and plug it into the solution. That means the second case. So your y2 of x, so this is x to the power 1/2, remember. So x to the power 1/2 times a0 plus a1 x, a2 x square. So a0 is something we already have, right? So a1 is something we just found here. So we plug in a1. a2 is something we found here. We plug it in here, a2x square, a3x cube, and a sub 4, x to the power 4 is a sub 1, a sub 2. So I'm being a little bit casual here, okay? So that's how you'd solve these problems, okay? This is kind of a lengthy problem, by the way, kind of a lengthy problem. Please don't get overwhelmed by it, okay? If it doesn't make sense, please go over the video a couple of times and look at the solution. I have typed it in everything here. Just follow the process, okay? Don't give up. Don't give up and don't be overwhelmed by it. If you see it a few times, it's gonna start to make sense. It's gonna be okay. All right, I hope that this discussion was helpful. Thank you very much.